Okay, ciao tutti, come state? Okay, good morning. All right. So, of course, this is when winter schools get real and we have the 9 a.m. lectures. So, thank you all for making it this morning. If it makes you feel any better, of course, California is 9 hours behind Florence. So, I'm hitting midnight right now. But I'm here nonetheless to enjoy the physics with you today. So, I want to pick up where we left off yesterday afternoon. Recall we had, I laid out the Hooft paradigm in analogy with the Landau paradigm. I gave you a justification for it that was intuitive in nature. Then, at least for ordinary global symmetries, I attempted to give you a sort of quasi-proof at the level of the normalized action or generating functional, so that you could really believe, why it was we asserted that quantum corrections respected the symmetries of the theory. Then we went ahead and we presented some successes, which indeed were some of the ones that motivated Hooft to formulate his original statement of the paradigm in the form of the chiral Lagrangian. We saw how spurion analysis beautifully allowed us to make predictions for the masses of the pions. And even once we introduced electromagnetism, which broke explicitly some of the global symmetries, we were able to use that successfully as well. So I want to. So that was, this is like Star Wars, right? So yesterday's lecture was like A New Hope, right? So we end on a high, and then The Empire Strikes Back starts, and it's all very bad. Okay, and then we have Return of the Jedi, and things get better. So this morning we're going to start with challenges to the Hooft paradigm. First, I want to start with challenges to the Hooft paradigm just within the example that we treated yesterday, the chiral Lagrangian. And then I want to go ahead and assess the Hooft paradigm throughout the standard model, in which it has some successes and some failures. I want to tell you about some other theoretical failures that people have just encountered, in the course of doing particle theory in the last decade. And that is where we'll leave it then with the challenges to the ordinary Hooft paradigm. Of course, the main point of these lectures is to develop a generalized Hooft paradigm. That requires us to broaden our notion of symmetries that might be relevant. And so we'll start to do that in the second half of the lecture today by introducing higher spin symmetry and seeing how that might help us to control additional quantities. Okay. So for some of you, going through this at least will be a lot of familiar things, although hopefully I can tell them to you in some new ways or with some subtleties you may not have thought about. And these things I hope will be genuinely original for everybody here. All right. So coming back to our example from yesterday, recall we said if we just thought about two light flavors of quarks in QCD, close to the scale of confinement, and we ignored everything else except the QCD interactions, we could make rotations of the left-handed up and down quarks into each other and the right-handed up and down quarks into each other. And formally speaking, right, those transformations are just the complex rotations of these two component spinners, which actually have full U2 symmetries rather than SU2 symmetries. But as we are often wont to do in particle physics, again, we stripped off the U1 factors. And so actually we just focused on the SU2 left cross SU2 right, which by hypothesis was broken by confinement down to the vector combination. And then we said, okay, we get 3 Goldstone bosons, and we went ahead and we pursued that analysis. But of course, we had ignored the other 2 U1 factors. We could call them U1 left and U1 right, but it's useful to make the 2 orthogonal linear combinations of them, which we would call U1 vector and U1 axial. U1 vector is actually the symmetry that is gauged by QED, so that's a good symmetry, and in fact, we used that secretly when we were doing the spurion analysis for turning on electromagnetism. U1 axial is actually part that would also be broken spontaneously by the VEV, the vacuum expectation value of the quark bilinear. And so nominally, this should also give us another Goldstone boson. Okay. Now, normally when people give you the chiral Lagrangian, they throw it out. Does anyone want to remind me why we throw it out and we don't try to figure out what the Goldstone boson is? Yeah. Good, that's right. So indeed, this is an example of something that now is the first point for today, which is that we can have global symmetries that are symmetries of the classical action, famously, but are not symmetries of the quantum theory. These are said to be anomalous symmetries. And this already is a challenge to the Hooft paradigm, because you'll recall the proof that I gave you yesterday, the quote-unquote proof, even at the level of ordinary symmetries, we assumed that the symmetry was a genuine symmetry of the quantum theory. We required invariance of the path integral, not just invariance of the action under the symmetry transformation. But if we have an anomalous global symmetry, then of course that's no longer true. All right. So indeed, just as a reminder, hopefully you've all encountered anomalies in your life as quantum field theorists, but just a brief reminder to help us all orient ourselves. As a particle physicist, you could do a very simple thing, and indeed this is how anomalies were first discovered by Jack Steinberger, is you could compute triangle diagrams of fermions in which you imagine one vertex is an insertion of the global symmetry current that you care about, and the other two vertices you can attach gauge bosons to. And this, if this diagram is non-vanishing, so this gets contributions from chiral fermions, it can be vanishing or non-vanishing. If it's non-vanishing, then we say the symmetry G is anomalous. And the consequence of this is non-conservation of the corresponding symmetry current. So instead of the current vanishing, we now get something which is proportional to in an appropriate normalization of the gauge fields, there's a loop factor, and then morally speaking, I'm going to be schematic here, there's a copy of the field strength and the dual field strength, FF dual. Okay, so this is just telling you that, classically this would be a good symmetry, quantum mechanically it's violated in this way, and other ways, of course, we could make the argument, maybe a more satisfying way of making the argument is not to say, oh, just sometimes there's a triangle diagram, you're out of luck. But if we had a symmetry that was a symmetry of the classical action, so the action was invariant under the transformation, in quantum mechanics, the place where the symmetry violation could appear in the path integral is in the integral over the measure. And so the Fujikawa derivation of the anomaly basically points out that we have to be careful when you do a global symmetry transformation on fermions to assess whether the measure in the path integral on the fermions is invariant or not. This is another way of arriving at the result. Okay. So famously, the UN axial symmetry in this case is anomalous with respect to QCD itself. So the divergence that we would get in this case for the axial symmetry is proportional to the field strength and the dual field strength of QCD. And this is a real threat because we know that when QCD grows strong at low energies, there's some non-zero expectation values, not just for quark bilinears, but also for all sorts of other bilinears, subsequent bilinears in the theory. And so necessarily, this is some really interesting violation of the current conservation. And that is in some sense what prevents us from treating this as an ordinary spontaneously broken global symmetry. And so for the most part, we typically throw it out. Now, of course, subsequently in field theory, if you're careful, you can actually figure out the consequences of this effect on the mass of the would-be Goldstone boson. We're not going to do that right now, but we're just going to point out that this is another loophole in Hooft's argument. And indeed, when Hooft wrote his original paper in 1979, he posited that the symmetries he was talking about were non-anomalous. They were genuine symmetries. Okay, so in some sense, Hooft has nothing to say about this case. There's actually a second anomaly that's living already in the example that we treated that somehow we're less bothered by, but nonetheless is present and interesting, and we'll come back to later on in these lectures. Does anyone, if we think about the chiral Lagrangian plus electromagnetism, is there one more anomaly that's interesting in this description? So I've given you a hint. Of course, we have QCD. That's this field strength. We said we turn on electromagnetism. That's another gauge group. So is there one more anomaly? Let me ask you another question. How does the neutral pion decay? What's its dominant decay mode? To 2 gammas. Where does that coupling come from? Good. So there's one more interesting anomaly with respect to electromagnetism. Here we've pointed out that this UN axial symmetry has an anomaly with respect to QCD. If we also, though, actually stared at this SU2 left and SU2 right, we say it's broken down to the diagonal. But of course, there is the diagonal combination, the vector combination, and then there's the orthogonal combination, which would be SU2 axial. And anytime you see an axial global symmetry, you should worry that potentially there's an anomaly. In this case, there is an anomaly. It's with the T3 generator of that SU2 axial. And that actually has an anomaly with respect to electromagnetism. And so indeed, there's a triangle diagram now where that T3 generator of the SU2 axial symmetry connects to 2 photons. Now, that generator, when the symmetry is, that SU2 axial is then broken by QCD confinement, that generator, of course, is the one that then corresponds to the neutral pion. So at low energies, you basically plug a neutral pion into this current, and this gives you the decay of the neutral pion to 2 photons. Okay, so that we're less concerned about. The reason we say, oh, that doesn't, that doesn't screw up the neutral pion as a Goldstone boson, that's because the density that it's proportional to in the anomaly is electromagnetism, all right, which doesn't have any non-trivial topology. It doesn't have any non-trivial expectation values, so that doesn't screw up our prediction for the neutral pion mass. But it does give an interesting physical effect. And even though the effect is not as violent as the anomaly with respect to QCD, you should still be made uncomfortable by it, right? If the Hooft paradigm is about global symmetries and we have anomalies, even for some relatively benign anomaly, you should be asking yourself the question, what is the surviving symmetry, right? What is the actual symmetry that's left in the presence of anomaly? And does that symmetry still control the form of counterterms? And as we'll see at the end of lecture 4, something very exotic survives actually in the presence of even this abelian anomaly. The true symmetry, the true global symmetry in the presence of this anomaly is something that's called a non-invertible symmetry. And instead of obeying normal group actions, it actually involves a fusion algebra. And so it's a much richer system than is obvious to us just from this casual inspection. And this is something that's really only been discovered and understood in the last 4 years. Okay, so we're really in the process of understanding what are the true global symmetries that survive anomalies. We'll make that definite in later lectures, but for now we should just be left with this feeling that there's clearly a loophole in Hooft's argument where anomalies are concerned.
Yeah. So with the action anomaly, what can we do in the chiral Lagrange? Are we just throwing it away, or is there a way of putting?
Yeah, of course. There's a way. Good. So the QCD anomaly. So there's of course is a way of estimating the corrections to the masses of the axial mesons that come from QCD. All right. So this dates back to Witten and Veneziano. Right. There's an interesting systematization of that, which is beyond the scope of what we'll cover today. Without going into that detail and talking more about the topology of the gauge theory in your normal standard model class, we of course just conveniently ignore it. Okay. But the punchline is there is a contribution to the mass of the mesons, which comes from, morally speaking, this expectation value. All right. Okay, so we should keep in mind that anomalies are present and they're interesting. We'll actually see this, I should say, is an example maybe of an anomaly that you've seen before. I'll call these anomalies ABJ anomalies or Adler-Bell-Jakif anomalies. These are anomalies where there's a global symmetry current insertion, and then it's connected to 2 gauge insertions. There are 2 other types of anomalies. One is where all 3 are gauge insertions, and that's just an example of anomalous gauge theory. We won't touch those very much because anomalous gauge theories have a pathology in the path integral. There's actually another class of anomalies, which is going to be in some sense the most interesting one we'll encounter, where there are 2 or 3 global symmetry insertions and then 1 or 0 gauge insertions. Now those don't do anything like this in the path integral, right? So they don't actually introduce physical pathologies. But if we carry out the imaginary exercise of gauging the global symmetries, as we did yesterday, it activates these anomalies, and it turns out it gives us non-perturbative constraints on the behavior of the theory as a function of scale. So those are known as Hooft anomalies. We'll talk about those more systematically later, but I just want you to start keeping in mind that anomalies are going to animate the rest of our lectures. All right. That's all I wanted to say then about the Hooft paradigm and the chiral Lagrangian. Now I want to turn to the standard model. Now, of course, these lectures are not about the standard model. Hopefully you've been exposed to the standard model again in your life as particle physicists, but because this is the first week of the winter school, we should at least say some things to get us all on the same page. So someone want to remind me, what's the gauge group of the standard model? Good. SU3 times SU2 times U1. Is that the local structure or the global structure? Do we know what the global structure? Sorry, I'm being glibly provocative. Do we know what the global structure of the standard model gauge group is? Good. So we don't. We're going to come back to this later. We actually don't know. This is in some sense the only thing that we know about the standard model gauge group is actually the algebra. Okay. We don't know what we call the local structure, the global structure of the gauge theory. That if that doesn't mean anything to you right now, that's fine. We're going to make it precise later on. But that's actually going to become a well-defined notion once we introduce higher form symmetries next lecture. All right, but at least if we look at local interactions, we know that this is the structure of the gauge group. Someone want to remind me, in conventions where all of our fermions are left-handed Weyl fermions in the standard model, what does one generation of fermions consist of? What are the fields? As I like to tell my PhD students, you should be prepared in life if someone breaks into your room and wakes you up in the middle of the night, shakes you awake and says, what is the standard model, right? You should be able to list the field content. Okay, so in case you have a hard time remembering, as I like to say, the standard model is cuddly. That is to say, the field content of one generation of standard model fermions is an SU2 doublet of quarks Q, the SU2 singlets U and D, the SU2 doublet lepton L, and the SU2 singlet E, right? So that's cuddly. There's 3 copies of this, right? Plus we have in the standard model the Higgs doublet, and that's it. And then the rules of the standard model are we write down, of course, all of the marginal and relevant couplings, so we want a renormalizable theory that are consistent with the gauge symmetries and involve the fields. Okay, and so when we do that, I just want to be schematic, but the structure of this Lagrangian is going to be important to us. So of course, it contains all of the kinetic terms for these fields. There's another set of terms we can write down for the gauge fields. So of course, the gauge bosons, the normal kinetic term, these all have the form of the square of the field strengths. So we have 3 of those. But we can also write down terms in Lagrangian, which have a coupling constant that I'll call theta. And then schematically, they're of the form F dual. And they typically have a normalization. So this, structurally is different. Now, of course, this term is CP even. This term is CP odd, and so this parameter necessarily would be CP odd. And we can, in principle, write down one of these for each of the 3 gauge groups in the standard model. So for SU3, SU2, and U1. Now, in practice, when we write down the standard model Lagrangian, we only write it down for QCD. So we only write down the SU3 version of this. We discard the SU2 version and the U1 version, even though they're all, in principle, allowed. Does anyone want to remind me why people normally throw out the SU2 and the U1 versions? The U1 is abelian, good. So what does that really mean? Well, you'll notice, of course, if you stare at these terms, so FF dual, it's easiest to see for an abelian term. So FF dual is just proportional to epsilon mu nu rho sigma, F mu nu, F rho sigma. And this, of course, with this anti-symmetrization, then we actually can see that this is a total derivative, right? Because I can take, this is just the anti-symmetric contraction of the derivative in the vector field. But now that I have the extra anti-symmetrization, if I could take one of the derivatives out of either of these and move it in front and get the same term. So this is clearly a total derivative. And so it's a surface term, right? And normally, we assume that there's nothing interesting at infinity. And indeed, for an abelian gauge theory in flat space, there is nothing interesting at infinity. Okay, so there's no boundary term. We can discard it. And so normally, we throw away the abelian version. All right. So that's why we throw away the hypercharged version of theta. Does anyone want to remind me why we throw away the SU2 left version of theta? Yeah. We can absorb it using field definitions. Good. I would say we can absorb it, we can modify it, render it unphysical using global symmetry transformations, and we'll make those global symmetry transformations precise momentarily. But indeed, by presumption in flat space, we can actually do rotations of the fields that would change the value of the coordinate for SU2 left, and that means that it has to be unphysical. We cannot do that for QCD, and so we keep that term. Now, why we can't do it for QCD, but we can do it for SU2 left, we'll see momentarily. It actually has to do with the structure of the rest of the standard model Lagrangian. I should also say one more thing, which is that actually when we throw away the hypercharge term, right, we're actually making a strong assumption. We're assuming that our theory is in flat space. And even if we are literally in asymptotically Minkowski space, I can put non-trivial objects into my theory, which effectively change the topology of space-time. So in particular, if I drop monopoles or string-like objects into the theory, in addition to the local particle excitations, that actually changes the effective topology. And in that situation, even an abelian gauge theory has non-trivial topology. So it's entirely possible that there are objects in the universe which are present and which prevent us from throwing away the total derivative. And that would actually render even the theta term for hypercharge physical. Okay, so when your lecturer throws away the hypercharge theta term, they're actually making a very strong assumption about the universe, and you should call them out on it. Okay. Of course, so this is sort of the kinetic terms for the ordinary fields, the gauge fields, this topological theta term. Then, of course, we have the Yukawa couplings. So we can write down, so there are 3 copies of this. So Yukawa matrices are all 3 by 3 matrices. Schematically, there are interactions that couple the up-type quarks with a 3 by 3 up-type Yukawa. There are ones that couple the down-type quarks in the down-type Yukawa, and then, of course, there's the left-time Yukawas, each of which are 3 by 3 matrices. And actually, the structure of these matrices will turn out to play a role in the fact that we can discard the SU2 left theta term, but not the QCD theta term. And then finally, of course, we have terms we can write down for the mass of the Higgs boson and its quartic coupling. And we're done. All right. So this is, I'm taking this definition of the standard model, the fields, the gauge degrees of freedom, and the renormalizable interactions. Of course, famously, this doesn't allow us to write down neutrino masses, and so that, in some sense, is physics beyond the standard model. For most of what follows, especially when we talk about the global symmetries of the standard model, I'm not going to pay too much attention to neutrino masses, but of course, they're there, and you'll hear about them in subsequent lectures throughout the school. All right. So if that's the standard model, let's now approach it with the spirit of the Hooft paradigm. And what we want to do is we want to look, so the standard model, when you actually go ahead, as we'll see, and you do all the parameter counting, even though nominally there's an enormous number of degrees of freedom here, many of them can be eliminated by some freedom to do field redefinitions. And at the end of the day, with our counting, there's 19 free parameters. And so the reason why the Hooft paradigm is interesting with respect to the standard model is then we can go through those parameters and we can ask, okay, some of them are small, and if they're small, do they respect the Hooft paradigm? That is to say, can we understand their smallness because there's a symmetry that's restored when they're set to 0? Some of the parameters are order 1 in natural units, so we don't really worry about them. And then some of them, of course, are small, but don't necessarily manifest a symmetry when they're taken to 0. And these are interesting theoretical puzzles that we would then attempt to try to explain in some other way. All right. So in some sense, if you think about physics beyond the standard model, you want to decide what's the best way to spend your time. If you have technically either Hooft natural parameters, ones that are small and are protected by a symmetry, they could have some interesting underlying explanation, but that explanation could live at the Planck scale. So you'd have no guarantee of experimentally testing your hypotheses. But parameters that are small and don't obey the Hooft paradigm, those are very interesting because those can't be explained by something that happens at arbitrarily distant scales. Whatever makes them small has to be happening at low energies so that it's not spoiled by quantum corrections. So in some sense, the reason why it's useful to think about the Hooft paradigm in the standard model is it helps us to focus our attention on maybe what are some of the experimentally most promising problems. Okay. Good. So if we wanted to do actually a counting of parameters, there's 19 parameters in the standard model. One way to do it is, of course, we have the Yukawa couplings of the quarks and the charged leptons. As we'll see momentarily, of course, in general, these are 3 by 3 matrices, but we can do field redefinitions, transformations of the fermions to eliminate many of the parameters and put it in a form where each of these is diagonal, plus there's one more price we pay when we diagonalize all of them, which is that we have the rotation angles and the complex phase that lives in the CKM matrix. Okay, and I hope that's familiar physics to you from your study of the standard model. So if we do parameter counting, okay, that means that we have the quark and lepton Yukawas. So those are the, let's call them the Q and L Yukawas. Those are some of our parameters. Again, there are just 9 of those if we've diagonalized all of these matrices. There are 4 CKM parameters, right? So those are the 3 mixing angles and the 1 complex phase. You could take the gauge couplings, so the gauge coupling of QCD, of SU2 left, and of hypercharge as parameters. We've said the only theta angle that we're going to keep is the QCD theta angle. And then, of course, we have the mass parameter of the Higgs boson and its quartic coupling. Okay. So that's our counting of the 19 parameters. Now, if we look at these, there's one sort of order 1 Yukawa among the Yukawas, which is the top Yukawa. All of the other ones are small, right? Starting with the bottom Yukawa, which is about 1 part in 20. Everything is much smaller. So there are many, many small numbers that live here. So that's a useful place to ask about the Hooft paradigm. The CKM parameters, similarly, they all start at sort of a fifth and get smaller in these rotation angles. Is the CP violating phase in the CKM matrix large or small as a phase? What is it as an angle in radians? So it's actually not, as an angle, it's not small. Okay. The reason we say that it's small is that the fact that there is a CP violating parameter in the CKM matrix is basically because we couldn't do enough transformations among the fields to get rid of all of the phases, right? But secretly, what does that tell us? That tells us that we had to know about the freedom to do transformations to all three generations of fermions in order to have a phase that survived. And so that means in physical observables have to have quantities that depend on mixing between all three generations in order to see the CP violating phase. So physical effects that come from the phase are small, but the actual phase itself as a phase is not small. Okay, so that's just an interesting fact, but it's worth keeping in mind. These couplings are all fairly large. They're all order 1, right? This is about a third. Everything is bigger at the weak scale, so that's not so bad. We only have bounds on it. So observables that it contributes to violate CP, and the most sensitive observable is the EDM of the neutron. And so we only have constraints on the neutron electric dipole moment, but this is less than about 10 to the minus 10, as far as we know. So this is a very, very small parameter. This is order 1. Okay, it's an order 8th, but that's not so small, so we're not going to worry about that. And of course, we'll come back to the Higgs mass momentarily. All right, but let's start with the small parameters up here. So the Yukawas, do the Yukawas respect the Hooft paradigm or not? Is their smallness protected by symmetries? This is not a trick question. You have a 50-50 chance of getting it right. Yeah. What's that? Oh, well, good. So, I mean, some of these, the electron Yukawa is 10 to the minus 5. That's very small, right? Everything except the top Yukawa is small in some sense, right? So they're small numbers. And the question is there a symmetry that's restored if we take any of the Yukawas to 0? Okay. What's that? Flavor, yeah, so indeed, there is. So how would we do a spurion analysis, right? How would we approach understanding the symmetries? We say, okay, let's set the Yukawas all to 0. And then ask, what are the symmetries of the fermions when the Yukawas are 0? So there's an enormous global symmetry. All right. Does anyone know what that global symmetry is? The symmetry of the fermions, 3 generations of fermions. The classical symmetry, we'll worry about anomalies later, if we set all the Yukawas to 0. I heard someone say U3 to the 5th. Okay. So let's start with that. So why U3 to the 5th? Well, so the 5th is coming from the fact that there are 5 types of fermions, which are distinguished by their gauge quantum numbers. For each one of them, there's 3 generations, right? So we have 3 left-handed vial fermions with the same quantum numbers. The rotations of those among each other is a U3 symmetry, and so that's why we get U3 to the 5th. Is this so that's the naive symmetry if we just turn off the Yukawas. Given everything that we've written down here, is this the exact symmetry, or are we overcounting by a small amount? Good. What's the U1 we've overcounted by? Good, good. So let me put it slightly differently. We've written down this as the gauge group of the standard model. Of course, that means it's a local symmetry. We could always choose to do a gauge transformation by a constant gauge parameter. That corresponds to the global symmetry that is gauged by the gauge group, right? So every time we have a gauge symmetry, if we ignore the gauge bosons, there's also just a global symmetry that acts on everything that's charged under the symmetry. So in particular, if we think about hypercharge, we could imagine doing a hypercharge transformation of all the charged matter in the standard model, where we simply set the transformation parameter to be the same everywhere in the universe. That's a global symmetry transformation, right? And that actually acts on all of these fields, right? So properly speaking, that's somewhere in here, right? There's a U1, which is the global symmetry transformation of hypercharge. And so in some sense, this is overcounting. Once we say that this is the gauge group, there's one U1 in here, which we've already counted over there. So we should take it out of our counting. All right, taking this quotient just says, we're gonna, this is the symmetry, but we've overcounted by the global part of hypercharge. Okay. Again, I told you we talk about the standard model, but I try to tell you some things that some of you may not have seen before. All right, so this is the proper global symmetry of the fermions when I turn the Yukawas to 0. And now, of course, when I turn the Yukawas on, I break this symmetry down by quite a bit. But already this tells us that the Yukawa couplings satisfy the Hooft paradigm. When I set them to 0, there's an enormous symmetry that emerges. Yeah?
Since the top Yukawa is so much larger than the other ones, wouldn't it make sense to use U2?
Good, absolutely. So if we then engage, so you're getting at an interesting point, which I really should have emphasized more even yesterday. You can ask the question, when does spurion analysis work, right? When I set these these parameters to background fields and then I follow them in the infrared, and I can really make good predictions when the spurions are small. If they're large, then the spurion and the square of the spurion, the cube of the spurion, they're linear combinations involving higher powers which transform in the same way as the spurion itself. And now if the spurion is small, those are negligible corrections and I can throw them away and make a good prediction. But if the spurion is order 1, they're all equally important, and then it's impossible for me to make a prediction, right? And so indeed, this is a crucial fact. The reason why the chiral Lagrangian worked with the quark masses is that they are small with respect to the scale of QCD confinement. And so indeed, so if we wanted to do a spurion analysis where we promote all the Yukawas to spurions, and then we see all the combinations that can appear in observables, powers of the top Yukawa, because the Yukawa is order 1, they're all equally important. So if we wanted to do a numerically precise spurion analysis to really use this as a strategy for doing calculations, we would indeed recognize that certainly in the up quark sector, one of the Yukawas is order 1, and so the good approximate symmetry, that's only broken by small numbers, is the U2. Absolutely, that's a good point. Okay. Yeah, so let's talk a little bit actually about how the symmetries are broken, just because it's instructive and it will actually help us to understand this question about why we threw away the SE2 left theta term. So we can ask to figure out, once we turn on the Yukawas, we're treating them as spurions, and we can ask that they transform in a way, right, that restores the symmetries that they break. So for example, if we're looking at the up-type Yukawa, normally we could do a U3Q transformation to the Qs, right, to rotate them, and we could do a U3U transformation to the Us to rotate them. But of course, generally those transformations, if this is a constant set of parameters, that would just change the theory as opposed to being a symmetry. So instead, we assign transformation properties to the Yukawas so that they compensate these transformations, and then this term becomes invariant, right? That's how a spurion analysis would work. If we want to see what symmetry is preserved when we set the Yukawas to their background values, we can ask, what part of the U3Q and U3U symmetries actually would leave one of these matrices invariant. So the first thing we do is we say, okay, let's use our freedom to do these transformations to diagonalize the Yukawas, right? All right. And then once we have a diagonal Yukawa, now we can ask, there's at least a subgroup of these U3 transformations that would leave the diagonal entries unchanged. Okay. So in general, if I have this U3Q and the U3U, I do those transformations, and this is a diagonal matrix, that will preserve a U1 cubed, right? It will preserve basically a correlated symmetry transformation of each of these that just acts on each diagonal entry, okay? So with respect to turning on, once I turn the up type Yukawa to its background value, okay, that's going to break the U3Q times U3U to 3 U1s, which just act on the three, again, the first, second, and third generation. The same thing happens with the down type Yukawa. That breaks now U3Q and U3D down to 3 U1s. But now there's one more wrinkle, which is we'd have 6 good U1s if these matrices commuted with each other, okay? But they don't. This is why we have a CKM matrix. And so actually, I can't separately do the transformations here and the transformations here. That would be using the same set of U3Q transformations twice. And so the fact that these matrices don't commute, of these nominal 6 U1 symmetries, actually only one of them is a true symmetry with respect to both Yukawas being turned on. So the combination of all of these that survives is just what we call U1 baryon number, because it acts in a way that up to normalization counts the number of baryons. actually, this is a slight overcounting, right? We said that the original global symmetry was U3 to the fifth, but it was overcounting a little bit of hypercharge. This little bit of hypercharge has a very small amount of overlap with U1 baryon. There's actually a discrete subgroup of hypercharge, Z3, which actually corresponds to part of what we would call these baryon number transformations. And so again, the existence of hypercharge means that we are slightly overcounting. Okay, so this is some of the global symmetry that survives once we turn on the quark Yukawa couplings. And then for the lepton Yukawa couplings, it's a much simpler argument, right? We just have, again, ignoring neutrino masses, we just have one set of Yukawas to diagonalize. And so that takes the U3 lepton and again just breaks it down to 3 U1s. And so our final accounting of the global symmetries of the standard model that are preserved once we turn on the Yukawa couplings is that we have this U1 baryon number modulo the slight overcounting from the overlap with hypercharge. And then we have 3 leptonic U1s. Very often people like to take the one combination that acts the same on all 3 generations. And so we'll call that lepton number. And then they take 2 more, which are just the differences between leptonic generations. Okay. So those are the nominal global symmetries of the fermions once we've turned on the Yukawas. I want to emphasize those are the classical global symmetries. Are they all good quantum global symmetries? No. Good. Why not? That's right. So actually, these there are anomalies now with respect to the rest of the standard model gauge group. The anomalies that actually are interesting in this case are anomalies with respect to SU2 left and hypercharge. In particular, you can compute the anomaly coefficients for U1 baryon and U1 lepton number. And it turns out, so again, what does that mean? That means if I do, say, a U1 baryon transformation, the electroweak anomaly now means there's a triangle diagram where now I attach either SU2 left gauge bosons or hypercharge gauge bosons. And what's interesting actually is the anomaly coefficient. So there's all 3 generations of fermions run in this loop. And so actually the anomaly coefficient for both SU2 and hypercharge is proportional to the number of generations. Okay? Now that's a very interesting thing. The number of generations appears in these anomalies. There's one more interesting fact, which is that the anomaly coefficients, the electroweak anomaly coefficients for U1 baryon number and this U1 lepton number are the same. Okay? And so what that means is actually we should take 2 orthogonal combinations of baryon and lepton number. We can take B plus L, which has an anomaly, and we can take B minus L, which has no anomaly because it cancels between the B anomaly and the L anomaly. Okay, so usually what we do in this case is we make the combination, again, not ignoring this overcounting for a moment, we make the combination U1B plus L and U1B minus L. This is non-anomalous and this is anomalous. Okay. All right. A couple of things. So we might say, okay, great, this is a good symmetry. Hooft can do his thing. These are good symmetries. They're just lepton generation differences. Hooft can do his thing. This is anomalous. Maybe we throw it out. It actually turns out there's still, without doing anything fancy like non-invertible symmetries, there's an ordinary subgroup of this symmetry which survives even in the presence of the electroweak anomaly. And the reason is, right, when we have an anomaly, we do a symmetry transformation of the fields, and we get some anomalous variation of the action, which is proportional to the anomaly coefficient. But because, in the path integral, the action appears as e to the is, if that anomalous variation is in the action, right, is proportional to 2 pi, then we actually haven't changed the theory. So there's often, when we have an anomaly, a discrete subgroup of the symmetry that survives, which it basically corresponds to doing a transformation by 2 pi divided by the anomaly coefficient. So because the anomaly coefficient here is proportional to the number of generations, there's actually a surviving discrete symmetry here, which is a discrete symmetry, a Zn symmetry, where n is the number of generations. Okay, so then there's a non-anomalous part of U1 baryon plus lepton number, which is a Z3 symmetry. And for those of you who study physics in the early universe, that actually is why sphalerons violate baryon and lepton number by 3 units, is because there's a surviving discrete symmetry. Okay, we'll come back to that later because it's one of my most interesting facts about the standard model. All right. One more thing, one more reason for doing this parameter counting is we said we would help us to understand why we don't write down a theta parameter for SU2 left. And the reason is, as we've seen, right, these symmetries are anomalous with respect to SU2 left and hypercharge. So if we do a symmetry transformation, a global symmetry transformation, the anomaly tells us we pick up a term that's proportional to these densities, right? And so that, morally speaking, shifts the coefficient of this parameter. Now, in the case of SU2 left, we can do one of these good symmetry transformations with the electroweak anomaly that would change the value of the SU2 theta parameter, and so that renders it unphysical. In the case of QCD, right, the global symmetry transformations that would change the value of theta in QCD are not in this good set. They're in the set that were broken by the Yukawas. So since they were broken by the Yukawas, if we attempted to do one of those transformations, sure, the anomaly would change this, but it would also change something in the Yukawas, right? Because the Yukawas are not symmetric under those transformations. And so in that case, we would just be moving a phase back and forth between the Yukawa couplings and the theta term instead of being able to eliminate it. Okay. So the fact that the global symmetries of the standard model that are anomalous with respect to QCD are broken by the Yukawas, that means this becomes physical. Whereas the fact that the corresponding theta term for SU2 left, that is anomalous with respect to symmetries that are preserved by the Yukawas, that means we have the freedom to eliminate it. Okay, so it's, very often people think like, oh, the Yukawas, it's some mess of some stuff, it breaks some symmetries, whatever. Okay, but like, the topological structure of the theory is actually very sensitive to everything. All right, that's, there's cool physics there. Okay, so I know this probably felt like a review of the standard model, but hopefully you learned some new things. And because we're interested in symmetries, now we're in a good position to really make some statements about the Hooft paradigm. So as we've seen, even given the anomalies, right, for the most part, the Yukawa couplings we can really understand as being Hooft natural because there's a large symmetry that's restored when you take them to 0. Same thing is true of the CKM parameters, which are just coming from the diagonalization of the Yukawas. These couplings we said are all order 1, so we're not going to worry about them. Of course, now we can worry about the rest of these. In particular, we'll worry about the Higgs mass and the theta parameter. Okay. I was going to also talk about custodial symmetry in the standard model. I think in the interest of time, I'm going to pass on just because it's a derived quantity from these. And so it's interesting, but I'll leave it in the lecture notes. All right. So now let's come to these last two terms and ask if they're Hooft natural, right? And as I said, this lecture is The Empire Strikes Back, right? So it starts with bad things. And so it must be the case that although the standard model has triumphs of the Hooft paradigm, it also has apparent violations. So let's start with the Higgs mass parameter. So unfortunately, the Higgs mass parameter, as we see here, it multiplies mod h squared. That's the square scalar. It's a complete gauge invariant. It has the same quantum numbers as the vacuum. And so, if we set the mass term of the Higgs to 0, there's absolutely no good symmetry of the theory, no global symmetry of the theory that is restored. We can go ahead and we can use, of course, our analysis, our spurion analysis based on dilatations, which we developed last lecture, and we can ask, what's the natural size, right? Given that if we treat the standard model as an EFT with a cutoff, then we should get contributions that transform under dilatations in the same way as the Higgs mass parameter. And that logic would tell us, there should be an order 1 coefficient times the one thing that transforms in the same way, which is the cutoff of the standard model as an EFT. So, naively, the Hooft paradigm tells us, right, that this mass scale should be proportional to whatever the scale is of the UV completion of the standard model. And that is something that we don't see in nature, right? We've, of course, only directly probed the standard model up to a little bit above the TeV scale. We have indirect probes to well above the TeV scale. And so far, we see no evidence of any dramatic change in the standard model. And so that suggests that the scale at which the standard model is UV completed is somewhat higher than the mass of the Higgs that we see. And so already this is now a challenge to the Hooft paradigm, right? There's a quantity that is small with respect to its natural size, but there is no symmetry that is emergent when we take the parameter to 0. So we cannot understand its smallness. Now, again, I said these lectures are not about naturalness. Lots of people want to claim there's no problem here because maybe the standard model doesn't have a cutoff as an EFT. And if you really took that claim seriously and you had to figure out how you explained all the physics of the universe without having some scale above the weak scale, you would have to try dramatically harder to make sense of that statement. So I'm happy to talk to you at coffee about the fact that this is a very serious statement and that the standard model really is UV completed at some scale, and this is an interesting problem. All right. Just as this, again, I've decided these lectures are about symmetries rather than solutions to this problem. But it is, of course, I wouldn't be doing my job if I didn't mention the two canonical approaches to solving this problem. This parameter on its own is not Hooft natural in the standard model. So the obvious thing to do is to say, well, maybe the standard model should be extended in such a way that there are symmetries that become exact when the parameter is taken to 0. That would render it Hooft natural, and then we would be OK. So there's basically two ways to do that. The first way is to say, well, we remember we saw in the strong interactions, right, that had a global symmetry, SU2 left cross SU2 right, which was broken down to the vector, and that gave us Goldstone bosons. And if there was no explicit breaking of those global symmetries, then the Goldstones would have been massless. And when there is explicit breaking of the symmetries, then their masses are proportional to the explicit breaking. And so the obvious thing to do is to say, well, maybe the same thing should just happen to the Higgs. Maybe the Higgs should be a Goldstone boson of some global symmetry, which includes the electroweak gauge group, that is broken by some other strong dynamics. Okay, so that idea that the Higgs is a Goldstone boson of some other strong dynamics, this is called the composite Higgs paradigm. And the basic idea is you have some new strong group which has a global symmetry. At the very least, that global symmetry, to be consistent with observations, it should include the custodial symmetry of the standard model. And when this group goes strong, this now is broken to the global part of the electroweak gauge group with custodial symmetry. And the counting of Goldstone bosons, the breaking of SO5 to SO4 would give you 4 Goldstone bosons, which is precisely the number of real degrees of freedom you would arrange into the SU2 doublet complex scalar Higgs. Okay, so this is the paradigm by which the Higgs is, in fact, the Goldstone boson of some spontaneously broken global symmetry. And then things that would give it a mass correspond to explicit breaking of this symmetry. Okay, so in this extension of the standard model, the Higgs mass parameter becomes Hooft natural, right? And we can understand its smallness. Now that has lots of interesting predictions, like there should be new strongly coupled states that are somewhat above the weak scale. We are looking for those at the LHC. We haven't found them. That doesn't mean this idea is dead, but it is currently in the phase of being experimentally tested. All right, so this is how the way in which it renders the mass parameter technically or Hooft natural. There's a second idea, which is, we've already seen that fermions, right? So the fermions in the standard model, they get their masses after electroweak symmetry breaking from the Yukawas. And we know that these masses are protected by chiral symmetry. We also saw that in the case of the chiral Lagrangian. So fermion masses we know are Hooft natural. The scalar mass is not. But of course, then the obvious possibility is, well, maybe I can introduce a symmetry to my theory, which relates fermions to bosons. And then I can have the Higgs borrow the chiral symmetry of a fermion mass that it's related to by this bosonic fermionic symmetry. So of course, that's what supersymmetry does. Again, the way in which it renders the Higgs mass natural is it says the Higgs is related by a new spacetime symmetry to some fermion. That symmetry also then relates the mass parameters. This mass parameter is technically natural because it's a fermion, and therefore the technical naturalness of the fermion mass is inherited by the Higgs due to this additional symmetry. So that is your back of a cereal box explanation of why supersymmetry is interesting in terms of making this Hooft natural parameter. Again, supersymmetry, we're looking for the LHC. We famously have not seen it. This is in slightly worse shape with respect to experimental data because it's a weakly coupled completion. And so the additional degrees of freedom, in some sense, should be closer to the Higgs than the strongly coupled degrees of freedom here. The game's not up, but it's it's certainly something that is in question with respect to experimental results. In fact, the last time I was here at GGI 13 years ago, I was a postdoc and I was asked to give lectures on the state of supersymmetry. And already in 2013, the state was not great. Okay, so that was like the most depressing lectures I've ever had to give, which is like, look guys, like this is not happening, okay? If you, of course, these are amazing and rich topics. They are worth week-long lectures in their own right. I would encourage you. There are many great lecture notes out there, and I'd be delighted to talk to you through the rest of this week about details of how these work, but it's not the focus of the rest of these lectures. Okay. Let's talk about one more. So again, this is a failing in the standard model. The obvious thing to do is to ask, can I extend the standard model with new symmetries that render it natural, and then I have predictions, all right? These are the two that people have used for a long time. Part of the purpose of the rest of my lectures is to say, well, what other symmetries could there be? And then we can start thinking about, can we actually bring them to bear on this problem? Now, I'll tell you right now, I don't currently know the symmetries that I'll tell you with the rest of the week. I don't currently know how to use them to solve this problem. But my hope is that by teaching you about these symmetries, you and I can talk about it, and then we'll figure it out. Okay. So I'm going to crowdsource this problem to all of you. All right. Let's talk about the last one of these not obviously natural parameters in the standard model, the theta parameter. So again, as we've said, it's a CP odd parameter. So it contributes to CP violating observables, in particular in the strong sector. And one of the most sensitive ones we have is the electric dipole moment of the neutron. Our current experimental bounds on that dipole moment tell us that this can be at most 10 to the minus 10. So I put this question to Jesse last night, so maybe I'll put it to all of you now. Is this parameter, so it's very small, is it Hooft natural? In other words, if we set it to 0, is there a symmetry of the theory that's restored? Sorry? CP? Is CP a good symmetry of the theory if I set theta to 0? No, why not? Mm-hmm. Right, we already broke CP, right? We broke CP in the weak interactions. We saw the CP violating phase in the CKM interactions. So theta, it's kind of a funny term, right? If you just said, if I just gave you a gauge theory and I said, here's this topological parameter, this theta term that violates CP, and I didn't tell you that you had all of this other rich structure, including the Yukawas, then indeed you would say it's Hooft natural, because if it's the only source of CP violation, setting it to 0 restores CP. And so you could argue for Hooft naturalness. But the question becomes richer because it's in the standard model where CP has now been violated somewhere else. And so now that symmetry is not restored, and so it becomes a little bit more challenging of a question. Now, the next thing we would say is, okay, so what were our rules, right? We'd say, in an EFT, if we want to ask, is a parameter, Hooft natural, the more elaborate thing would be to say, well, this transforms as a spurion with respect to some symmetries. It should get corrections, a reasonable thing to expect is the size of corrections to this, right, from quantum corrections, should be generated by other parameters that violate the symmetry in the same way, in particular, the CP violating phase in the CKM matrix, right, which also violates CP. So this is not a small angle, right? So if this were the relationship, then this would obviously be a huge problem. But as we've said, right, in order to have a physical CP violating parameter in the weak interactions, we needed to be able to exhaust the rotations of all 3 generations of fermions. And so that means in observables, this appears with products of small mixing angles between different generations, right? So that's why observables actually have a small factor out in front, which is, like 10 to the minus 5, all right, from the Yarlskog invariant. And so actually, if you go ahead and you try to ask, let me compute a bunch of Feynman diagrams to ask at what order I get a divergence that would cause this angle to feed into this angle. And the answer is the first contributions are finite at 3 loops. And the naive size of them as a contribution to theta is somewhere in the order of 10 to the minus 18. So, all right, so first it seemed bad. We'd broken CP somewhere else, so we can't rely on technical Hooft naturalness. But then if we ask actually what size of radiative corrections does this generate to that, because of all this suppression from loop factors and multiple generations, that number actually is very small compared to our current bound. So then it's less of a problem. Okay. So, is it Hooft natural? Is it technically natural, right? It's still radiatively stable. It's only getting corrections from something else that's very small. Maybe it's okay. But I would say there's one other thing which kind of makes this parameter troubling for people, and this is why people spend a lot of time these days thinking about possible deeper explanations, which is that if you ask, at the level of if I wanted to express this in terms of Yukawa couplings, this phase, right, is the argument of the determinant of the difference between y up, y down, and y down, y up. Okay, that's how we get a CKM phase, right? It's a statement that these matrices are not simultaneously diagonalizable, and so there's a phase that lives in that difference. Okay. The theta parameter, we actually wrote the theta parameter in front of QCD, but we've already noted, right, there are parts of the flavor symmetry of the standard model actually do have an anomaly with respect to QCD. They're just ones that are broken by the Yukawas. So we could do a rotation of the fermions that would change the Yukawas and change the value of theta. And that means for the QCD theta angle, right, there's a linear combination of the term that appears in front of GG dual and a term that is proportional to the quark mass matrices. And that's actually the physical strong CP violating parameter. That's what we call theta bar. And so the actual combination that's physical is whatever the term is that you've written in front of GG dual. And then there's a piece which is whatever phase is living in the Yukawas that has the anomaly with respect to QCD. And so this is arg det y up, y down. Sorry. And the reason I mention this is that, okay, we've said, you know, it's not exactly Hooft natural because we broke CP elsewhere. However, this CP violation feeds in by a very small amount. But imagine you're now writing down a microscopic theory that gives us the standard model at low energies. Somehow, when you write down that theory, you have to find a way to put a CP violating phase in this combination of the Yukawas without putting a large CP violating phase in this combination of the Yukawas, right? But these are not so different. And it turns out it's just very hard, especially if you try to actually build a model that puts a phase in this combination but not this combination. You have to work incredibly hard. So there's something about trying to make a small theta parameter in the microscopic theory that is just difficult because the structure of the CP violation is so similar between the theta angle and the weak CP violation. Okay, so that's why, you know, the theta parameter has a sort of intermediate status. It's kind of Hooft natural, it's kind of technically natural, but if you try to write down a theory to explain why it's small even in the far UV, you get into this funny situation where the CP violation sources are not that different from each other. And it's hard to write down a theory that puts an angle here, but not there. So this is why people try to solve this problem. In some sense, these days, they try even more than trying to solve the explanation for the Higgs mass. And indeed, if you're doing particle physics in the US right now, basically everybody is trying to solve this problem. Okay, they more or less gave up on the Higgs mass, but they're like, well, this one's an interesting problem. I just want to mention briefly, of course, the most popular solution because it will actually come up later when we talk about generalized symmetries, higher form symmetries. It's one of the most interesting ways of sort of giving life to the properties of higher form symmetries, which is the axion solution to this problem, the strong CP problem. And the basic idea behind the axion solution to the strong CP problem, let's see if I can say it in word level, is if you actually go ahead, if you turn on this theta term in QCD, right, so it's a term in front of GG dual, and then you follow the chiral Lagrangian down to low energies, you find that the vacuum energy of QCD as a function of the theta parameter goes like, crucially, minus things that depend on the pion mass and the pion decay constant, and then at leading order, it just goes like cosine theta. Now, of course, you know, so this is interesting. This tells you that you would minimize the vacuum energy if this angle were 0. That doesn't solve the problem because theta is a parameter. It's not a dynamical variable, right? This just says whatever theta is, there's a contribution to the vacuum energy of this form. But now there's a sort of obvious idea, which is that if you managed to, instead of just having a theta term in front of GG dual, if you managed to couple a field as well, so it would have to be a pseudoscalar to correspond to the CP violating properties. And since this is dimensionless in natural units, we have to make this dimensionless. If we had a field that coupled in this way, then of course, when we follow this down to low energies, we would now shift the vacuum energy by an amount that depended not just on the background value of theta, but also on this field. And now this is a potential for the field. And so, of course, it wants to minimize its potential by canceling off whatever the bare theta term is. Okay. So this is the axion solution to the strong CP problem. As I've said it probably seems contrived to just pop a field here to do your dirty work, but it actually turns out to be very easy to write down a model where in the low energy effective theory, this is what happens. Okay, so this is the way that you would solve strong CP, basically by making the theta parameter dynamical, and then the structure of the QCD vacuum energy is such that it wants to minimize the energy at the CP preserving point where the effective theta angle is 0. All right. Again, axion physics, of course, is very popular these days. We're going to revisit the axions as a way of understanding the generalized symmetry structure of the standard model and its extensions. All right. So those are challenges to the Hooft paradigm in the standard model. I want to give you a couple more examples of challenges that we found just in theory, and then I want to start talking about how we would generalize the Hooft paradigm to fix all of these things up. So let me give you 2 examples. These are now theoretical violations of the Hooft paradigm. What do I mean by that? Well, this just says, even in a weakly coupled quantum field theory, you can follow this logic and you can say, well, some parameters should be connected to other parameters by quantum corrections. That's, all the things that transform in the same way under the symmetries should be related by loop diagrams. And then in some cases, you actually go ahead and you calculate the diagrams and you find that they're not connected, even though they transform in the same way under the symmetries. So there's apparently a violation of Hooft naturalness because it's telling you that things that are transform in the same way, nonetheless actually don't feed into each other. Okay. So these are theoretical violations of the Hooft paradigm. And some of them we think we know how to explain, and others we really don't know how to explain. So these are just, in simple perturbative examples, some interesting puzzles that we would actually like to bring under some envelope of a generalized Hooft paradigm. So let me give you 2 of them. One of them they both pertain to thinking about the standard model as an effective field theory. So when we wrote down the standard model, we said, okay, we're going to say the interactions are just the renormalizable ones. But we know the standard model is not the complete description of nature, so we should treat it as an effective field theory. And if we wanted to treat it as an effective field theory, the way we would do that, so of course, the standard model EFT we call SMEFT. The idea is to say, okay, well, we start with the renormalizable theory, and then the rules of effective field theory are we can add irrelevant operators to this, which are just all of the gauge and Lorentz invariant functions of the low energy fields. And that is now what defines, in some sense, our EFT. So now we would add operators whose dimensions are greater than 4. Each of them has a Wilson coefficient. They, of course, all, if we make this dimensionless, they all come with some UV scale that suppresses them. And each one of those multiplies all of the different operators we can write down. Okay. And of course, the reason this works, right, in principle, there's an infinite number of these operators, but as we go up in the operator dimension, they get suppressed by more and more powers of a UV scale. And so at low energies, with a fixed precision, we can afford to truncate this expansion at some point, and that's how we can still make predictions, even though there's formally an infinite number of terms. All right. So you can go ahead and ask, the first operators appear at dimension 5 and dimension 6, and we can go ahead and write them down. At dimension 5, right, there's sort of one interesting class of operators that we can write down. Does anyone want to remind me what that is? The Weinberg operator. All right, good. Okay, so everyone knows about neutrino masses. So dimension 5, right, famously, we can take HL and square it. That's a dimension 5 operator. If we put the Higgs to its background value, this gives masses to neutrinos. So this is a great way of understanding some of the physics beyond the standard model. And again, this is very compatible with the Hooft paradigm. Neutrino masses we know are very small, but they're actually an accidentally forbidden property of the renormalizable theory. They can only appear as an irrelevant operator, and so that means they are automatically suppressed by some scale. So that's a good success of the Hooft paradigm. If we go to dimension 6, of course, there's a lot more operators we can write down. Famously, there are 59 independent operators with one generation of standard model fermions. There's more than 2,000 once we include all the generations. I'm not interested in enumerating those for you, but actually I want to use this as an example of a violation of the Hooft paradigm. So you would expect, right, there are lots of operators we can write down at dimension 6 that have the same symmetries. And so we would expect, right, that we should be able to take one of those operators and dress it with renormalizable standard model interactions to make a loop. And that should have a divergence in it. and have the structure of some other operator. And so when we normalize the theory, this gives us anomalous dimensions that cause the operators to mix, right? So our expectation from the 't Hooft paradigm is if I have two operators that transform the same way under all the symmetries, I should be able to take one of them, make a loop diagram that has divergence in it, and that should normalize the other one. And then that means as a function of scale, this operator will be generated by that operator. Okay, this is a completely consistent expectation from the 't Hooft paradigm. So actually in 2013, for sort of funny reasons, once we discovered the Higgs, we decided we should really get serious about the standard model EFT. And people actually started computing this matrix of anomalous dimensions. And they found something bizarre. They found that in many cases, even when two Wilson coefficients had corresponded to operators with exactly the same symmetries in the standard model, the anomalous dimension was 0. Okay. So to give you one example of this, you could consider an operator that has the form a field strength squared times the Higgs squared. Okay. So as a contact term, right, that would have at the lowest order like 2 gauge bosons and 2 Higgses coming out of it as a dimension 6 operator. And that has the same symmetries as operators that are of the form sort of 2 derivatives and 4 Higgses. So if you wanted to write it out explicitly, that could be an operator like the derivative of h squared squared. That's a 2 derivative 4 Higgs operator. Okay, so this would be something that just has 4 Higgses coming out of it, but they're derivatives acting on some of the lines. All right. Now, there's no interesting symmetries, even the spurious symmetries of the standard model, that distinguish these operators. They both respect all of the flavor symmetries and custodial symmetry, everything. And so it seems reasonable that if I started with this operator, I should be able to close a standard model loop and give us this operator. For example, I could just use normal couplings of the Higgses to gauge bosons, right, to make this loop diagram. And this, generally speaking, should have a logarithmic divergence in it. And so when I renormalize the theory, I should find that I generate that. Okay, this is an example. So you go ahead and you calculate these diagrams, and you find, in fact, that there's no divergence here. So this operator does not feed into that operator. And so it violates this expectation. And that's very surprising. That means I can turn on this operator in the theory, and at least at one loop in perturbation theory, it does not generate something that has the exact same symmetries and for which Feynman diagrams exist. All right, so it turns out this is not the only example. There are many, many zeros in this matrix of anomalous dimensions, which all have this puzzling property. And the thing that's even more surprising, so for a while people thought, oh, this is just a 1 loop accident, like everything is going to be connected to each other at 2 loops. We've now found that zeros exist at 2 and 3 loops. They could also exist at 4 loops. It's just no one has taken the time to go ahead and check. Okay, and so there's actually a sign that there's dramatically interesting selection rules that are operating here, and we have absolutely no idea why with respect to the ordinary symmetries. Okay, so that's just a theory violation of the naturalist paradigm that we've seen just by thinking about the standard model as an EFT. I want to give you one more example. This is about the running of Wilson coefficients into each other. You can also ask about the actual generation of the Wilson coefficients. That is to say, when you construct an effective field theory, right, we said, if you have a perturbative example where you know the microscopic theory, and you construct your EFT, you can fix the Wilson coefficients in the EFT by asking that the EFT reproduce the full theory's predictions at low energies, right? And so that's doing a matching calculation. And so that amounts to being able to actually compute these Wilson coefficients at some UV scale, starting with some specific microscopic theory. And again, you would expect that in situations where whatever interactions the UV theory respects or violates, that should be reflected in the Wilson coefficients that you generate when you do the matching calculation. In particular, whatever symmetries you violate, you should generate the Wilson coefficients in the IR that violate the same symmetries. And there was actually a famous example that was worked out by Nima Arkani Hamed and Kaisuke Haragaya about 4 years ago. They were actually ambulance chasing the muon G-2, right, back when we thought that this was a deviation from the standard model. And they were asking, what's the simplest model I can write down where I add some new particles and I integrate them out and I generate the dipole operator? And they went ahead and they wrote down a model and they did the matching calculation and they got 0, okay, for the leading contribution to the dipole operator. In the interest of time, I'm just going to leave the example in lecture notes. Again, I'll ask the organizers to distribute my notes at the end of this week, so you can go ahead and read about it in more detail. But it's another interesting example where the dipole operator should be generated if you just look at all of the ordinary symmetries in the UV theory, but you actually do the matching calculation, and it's 0. And there's really no way to understand it completely from the symmetries of the theory. There are more other peculiar properties of that example that we really don't understand. So again, these are simple things, perturbative calculations, but they appear to be violating the paradigm. Okay. So the Hooft paradigm, hopefully we've gone through this saga where we started to think it was a good idea. We had lots of justification that turns out to be borne out beautifully in nature. And then we have all of these cases where despite those successes, it also appears to fail. It both fails experimentally and it fails theoretically in places we can calculate. And so this is the point where the Hooft paradigm starts to feel like the Landau paradigm did about 10 to 15 years ago, which is a good idea in some cases, but something that maybe it starts to feel like we should throw out the window. So now the point of the rest of these lectures is, well, we've treated the Hooft paradigm as Hooft invented it, 47 years ago, with the symmetries that he knew about at the time. And since then, we've just learned about the existence of dramatically more symmetries, even in 3+1 dimensional quantum field theories. And it's a reasonable thing to ask, if we bring all of those symmetries to bear to define a generalized Hooft paradigm, can we actually start to understand or incorporate many of these exceptions and bring the Hooft paradigm back together as a way of thinking about the universe? So my goal for the rest of these lectures, starting now, is to start to tell you about these newer symmetries. And I want to say, throughout these lectures, I'll try to persuade you that these new symmetries do address many of the shortcomings that I've already presented. Now, again, I don't know how to explain the Higgs mass with these symmetries. I'm hoping you'll help me do that. But even if you don't care about what these symmetries mean for the Hooft paradigm, I hope that by telling you about you'll find them useful in the rest of your life in particle physics, because they're very interesting and they allow us to do very interesting things. And this is part of, I think, a greater message that I think is important for the particle physics community, is in a lot of particle theory these days, we're taking the rules of quantum field theory as Hooft and Weinberg gave to us 45 years ago, and we're just rearranging them in different ways. But a lot has happened in our understanding of quantum field theory in those 45 years. And so as particle theorists, we want to take these new developments and use them. Okay, so that's really, if nothing else, hopefully the message that you take from the rest of these lectures. Okay, so the first symmetry example I want to give you in the next 20 minutes, and then I want to make sure you have nice time for coffee before we turn things over to Jesse, is higher spin symmetry. And again, in the interest of giving credit where credit is due, this is a point that I first saw, and as far as I know, was first made systematic for spiro analysis by Riccardo Rattazzi in his GGI winter lectures in 2021. If you want to go read about it, he buried the same physics in an appendix with a paper a couple of years ago. Again, I'll leave that in my lecture notes. What I'm going to do is I'm going to give you a version of his story, and then I'm going to add my own ingredients to it, which help to show that it may be powerful to start explaining some of the things that we've already seen. All right, so what is higher spin symmetry? So just as a motivation, right, we said when we do a spiro analysis, like we did for the Yukawa couplings in the standard model, what we do is we turn the interactions to 0, right? We saw what global symmetries emerged, and then we used spiro analysis in them to figure out the consequences. But if I turn the interactions in a quantum field theory to 0, all of the interactions, so I just get a free theory, I don't just get all of those nice global symmetries, I actually get an infinite dimensional symmetry group, which is known as the higher spin symmetry. To show you what it is and to demonstrate how we can do a spiro analysis with it, I just want to consider the sort of simplest possible example in 3+1 dimensions, which is 5-4 theory. Okay. But I want to emphasize this symmetry is a good symmetry really of any free theory of vectors and fermions and scalars in 3+1 dimensions. And so it's not special to the example. It's just that this example is the best way to illustrate how it works. Okay, so let's just take the free theory, right, which is just consists of the kinetic term and the mass term. If we wanted to, right, there's another interaction we could write down, which is the phi to the 4th interaction. So what we're going to imagine is we're going to turn this off. We're going to ask what is the infinite dimensional symmetry here, and then we're going to ask, can we use it to do a spiro analysis with respect to this coupling? Okay. So to see what the symmetry is of the free theory, it's actually much more obvious to go ahead and take the theory, do the Fourier transform, and take it to momentum space. And in that case, right, the action that we have, of course, we have the integral over d4p. We have our factor of a half. And then in momentum space, I'll write the twiddle to indicate that we've taken the conjugate momentum space version of the field. The covariant term just turns into a p squared. We get the mass squared, and then we multiply 5p. And the reason why, just to remind you, the reason why we got 5 minus p here is that phi is a real scalar field, and so when we do the Fourier transform, that satisfies the property that phi star of p is equal to 5 minus p. All right, so that's where this came from. All right, so and crucially, even though this was a real field, right, now we've done the Fourier transform, so this is now a complex field in momentum space, but it obeys a constraint. Okay, so in momentum space, we can actually now imagine doing rephasings of phi. So the rephasing of phi that we're interested in doing is taking phi and multiplying it by a phase which itself can be a function of momentum. So we'll rotate it by e to the I theta of p. And this is a symmetry of the free theory, provided we satisfy a constraint. So theta of minus p has to be equal to minus theta of p. That is to say, theta has to be an odd function of p, right? The reason that that works, of course, is that if that's true, right, then the rotation of phi of p and of phi of minus p, those phases will cancel. Okay, so that's the important restriction, is that this is an odd function, but otherwise there's no further restrictions on it. Okay, so now we can go and follow a Noether procedure, right? We've claimed there is a transformation I can do on the fields that leaves the free action invariant. In particular, infinitesimally, right? The variation of the field is just I times theta of p times the field itself. Okay, so you can go ahead, and then of course, also using the fact that this is an odd function of p, if we wanted to, we could then expand this as a polynomial in powers of p. And so in general, it's a sum over odd terms of some coefficients, right? So there's some, depending on how we want to normalize it, there are various coefficients, which are anti-symmetric coefficients that are multiplying these odd combinations of p's. All right. I'm sorry, I made a misstatement here, which is quite important. So the p's, of course, are indistinguishable, so this is necessarily a symmetric coefficient. The oddness of the function comes from the fact that it depends on odd powers of p. Okay, so crucially, this is symmetric. All right, so we can take this back. This is a momentum space statement. We could take this back to position space, and we could ask, what is this transformation of the fields in position space? And it corresponds to being, so with the Fourier transform, we'll pick up a minus sign. Again, it's a sum over odd powers of terms. Again, we have this normalization, and we have this symmetric parameter. And now the Fourier transform takes the powers of momenta into space-time derivatives, acting on the fields. Okay. So this, this is something actually, if we look at low powers in this expansion, this is something that we already know about. In particular, right, if you take the first non-trivial term, so s is equal to 1, where you just have one space-time derivative acting on phi. Does anyone recognize what that symmetry is? If you just took the first term in this expansion, S is equal to 1 term. Yeah. It's translations, right? Good. So indeed, so that's a symmetry we already know about. And the corresponding Noether current, right, following the Noether procedure is just the stress energy tensor. It's just T mu nu. But so that's a familiar symmetry. But now what makes this an interesting non-trivial symmetry of the theory, a higher spin symmetry, is now we have all of these higher terms, which have their own higher index conserved currents. In the lecture notes, I've gone ahead and constructed the 4 index conserved current corresponding to the S is equal to 3 term, the next non-trivial term in this expansion. Okay. And all of these currents that you construct via the Noether procedure from this variation, they're conserved on shell, so when you use the equations of motion. Okay. All right, so how are we going, so we've said this theory has an infinite dimensional symmetry. When we turn all the interactions to 0, that's much larger than the ordinary zero-form symmetry. The first part of that symmetry is something that's already familiar to us, the symmetry of translations, but all of the other terms are really an exotic higher spin symmetry. And so now the question is, how can we put that to work, right? We've said the spirit of a Spurian analysis is to say we see a symmetry that emerges when we set a parameter to 0. Maybe that symmetry then controls radiative corrections to the quantity of interest. But to make that productive, we have to say, now if I turn on the parameter that violates the symmetry, I have to be able to treat it as a background field that transforms covariantly and do a Spurian analysis. Okay. So what I want to now do is see, can we do this now for the infinite dimensional higher spin symmetry? Can we actually treat this quartic coupling, which violates the symmetry, as a spurion? And then can we learn anything interesting from that analysis? Okay. So it's very hard, actually, if you figure out a nice way to do it, please tell me about it. It's very hard, actually, in position space to do this spurion analysis. But it's relatively straightforward to do a spurion analysis in momentum space, where the transformation of interest, right, is just this nice rephasing of the momentum space modes. So let's take, just again, this example of phi-4 theory and ask how we could go ahead and do a spurion analysis. So one thing I want to note is this higher spin symmetry is a symmetry either of the massless or the massive theory, right? As we've constructed it, really both the kinetic term and the mass term are invariant with respect to it. For the spurion analysis that I'm about to do, I actually want to make a slightly different choice. I want to say, let's imagine constructing just the higher spin symmetry of the kinetic term, okay? And then actually we're going to treat both the mass term and the quartic interaction as spurions that violate the higher spin symmetry. All right. So what would that look like? Well, if we take this Lagrangian density, we've already written the free part in momentum space. But let's write both the mass term and the quartic coupling in momentum space. And so what that gives us is pulling out our factor of -0.5. For the mass term, right, we have the momentum integrals for both P1 and P2. And normally, if we just wrote this down in momentum space, we would have a factor of 2 pi to the 4th. We'd have a momentum conserving delta function. We would have the mass parameter as a constant. And then this would be multiplying the Fourier modes, phi at P1 and phi at P2. Okay. And similarly for the quartic interaction, right, we would have the normalization. All right, I haven't given a normalization here. It would just be the integration. Now we would have 4 of these integrals, right? We would now have momentum conserving delta function for all 4 of the momenta. We would have the constant quartic, and then we would have 4 powers of the fields. All right. So, clearly, for example, this term in momentum space, it violates the higher dimensional spin symmetry. because if we did the rephasing of each one of these four components, even using the momentum conserving delta function, those variations would not all cancel, right? But we can now do a spurion analysis simply by asking, let's impose that the quartic coupling transform in a way that compensates the variations of the fields that then would render this entire term invariant. And so we can see by inspection, for example, the way that the mass term and the quartic would have to transform in order to preserve the spurionic symmetry is if we imagine promoting the spurions, which depend on the momenta that appear there, we would restore the higher spin symmetry of the massless free theory in this case if we treated the mass parameter as a spurion that transformed in a compensating way. And similarly, if we treated the quartic coupling as a function of the momenta that transformed in a compensating way. And with those spurionic transformations, right, now if I do a transformation of the fields and I do a transformation of the spurions, then the action, including the interaction terms, remains invariant under the higher spin symmetry. And then, of course, at the end of the day, we would set these to their background values, and we would regain the theory that we actually are interested in. OK. So what does this do for us? Well, one thing it does, actually, is it improves kind of our expectation of a Hooft naturalness that we already built for example, mass parameters just using dilatations. Right? So if you'll recall so far, by using dilatations, we said, based on the spurion analysis with respect to dilatations, that mass parameters transform in the same way as cutoff squared. And so that gave us a natural expectation. But if we actually wanted to go ahead and do a calculation, for example, in this theory, and we treated this as some EFT with a hard cutoff lambda, and we wanted to compute quantum corrections to the mass, they would come, for example, from Feynman diagrams that require us to use the quartic interaction, right? So we would get, for example, a quadratic divergence here, and this would tell us that the mass of the scalar should get a contribution that goes like the quartic times the cutoff squared, right? So crucially, interactions were required to correlate the mass parameter with some UV scale. And that is not present in our spurion analysis using dilatations, right? Dilatations missed that. And indeed, this argument would be wrong if we just had a free theory, because nothing requires quantum corrections to feed into a mass. Somehow, the coupling was important. So that is something that this spurion analysis in the higher spin symmetry buys us. Because we can now, treating the mass as a spurion, we can say, OK, given that this transforms in a certain way with respect to the rephasings, what other quantities in the theory are covariant as spurions in the same way? Well, one thing that's covariant in the same way is if we take the quartic coupling, we take, say, the first two components of the momentum in that quartic coupling to be the same as the ones that are running through the mass term. And then the other two are free. Because this is going to be appearing with a momentum conserving delta function, the other two are free, but they have to compensate each other. Okay? So they can be anything you want as long as they're equal and opposite. All right, so this now is a spurion for that infinite dimensional spin symmetry, transforms in the same way as a mass parameter. And so we know that this should be able to feed into that. And so indeed, if we couple the spurion analysis for the higher spin symmetry with the spurion analysis from dilatations, we get exactly the right answer. The cutoff squared comes from the spurion analysis and dilatations, and the coupling comes from the spurion analysis of the higher spin symmetry. Okay. Now, also the fact that here I have the right spurionic transformation if these are equal and opposite. Okay, that tells me they can be anything I want. Effectively speaking, in the diagrammatic language, that's equivalent to the integral over all possible momenta running in this loop. These momenta can be anything you want, right? So the spurion analysis, in some sense, it's translating properties of Feynman diagrams into the language of symmetries. And you could say, look, Nathaniel, I didn't need this fancy analysis in order to be able to tell you what this loop diagram is. But it is very useful that things that appear to be properties of just Feynman diagrams, we can now phrase as a symmetry. And again, this makes a generalized Hooft paradigm, which includes the higher spin symmetry, more powerful. I want to give you one example. So this is something that already Ricardo would have told you in 2021. It's kind of nice. It just makes this Hooft expectation more complete. I want to tell you one more thing that you can use the symmetry to understand, which explains a funny fact that you presumably encountered when you first learned quantum field theory, but maybe never really had a good explanation for, which is there's a famous result that again appears to be sort of a violation of the Hooft paradigm, which is that in this very simple phi-4 theory, the masses were normalized at one loop. In fact, we just saw why it is, right? There's a one loop diagram that connects the mass. But the kinetic term is not renormalized until two loops, right? So if you go ahead and you renormalize the theory and you compute the divergences at one loop, you find that they can be absorbed purely with a mass counter term. So the mass is renormalized. But there's nothing that's proportional to p squared. And so there's nothing that renormalizes the kinetic term. So already this is kind of a violation of the Hooft paradigm, right? There's the mass term and the kinetic term, generically speaking, with respect to the ordinary symmetries, they both transform in the same way. So they should presumably get corrections in the interacting theory at the same loop order. But that's not something that we can understand, again, using the ordinary symmetries. Okay. But this Spurian analysis now actually allows us to figure it out. In particular, right? So I want to ask, things that in general have the right spurionic transformation to correct the two-point function. Okay, indeed, in the interacting theory, it's insertions of this quartic interaction where these momentum lines are the momentum lines that we pull out in the two-point function, and these can be anything we want. But crucially, they're independent of the external momenta, right? That's a property of the spurion analysis. So now you want to say, okay, so maybe using this spurion, there'll be some divergence that'll contribute to the renormalization of the two-point function. And in particular, it's the divergent part that's going to give me the renormalization. The divergent part is coming from the sum over these momenta, but because these momenta don't depend on the external momenta, that already tells you, right, that at one loop, the two-point function gets no divergences which depend on the external momenta. All right. Therefore, there's no wave function normalization. So already this spurion analysis tells you there's no wave function normalization at one loop. Now, there is room to have wave function normalization at two loops, again, just using the spurion analysis. That's because at two loops, if I want to have something that has the right momentum dependence to correct the two-point function, I can use two insertions of lambda. One of them can give me one of the external momenta, and then in principle, I have three arbitrary momenta that I've not pulled to the outside of the diagram. I have a second insertion that can give me the other external momenta. In principle, now this can have compensating momenta. And then finally, the fact that every time one of these appears in momentum space, it has a momentum conserving delta function, that actually tells me I don't have these sets of three independent momenta. I actually only have two independent momenta that I can sum over. And then the third momenta actually has to depend on P1 and P2 in each of these diagrams. And so what that now means is, what I'm summing over here to give me the divergent structure does depend on the external momenta, and so it does give me wave function normalization at two loops. So the spurion analysis is powerful enough to explain the fact that in phi-4 theory, there's no wave function normalization at two loops, even though there is mass normalization at one loop. Now, a reasonable skeptic in the audience would again say, I've just repackaged things that are already apparent in Feynman diagrams in this language. So I'm not saying that I've learned a new fact about the theory. But what is interesting to me is that we've been able to translate things that previously seemed like weird facts about Feynman diagrams into statements about the higher spin symmetry of the theory. And that is interesting because it brings diagrammatic facts into the umbrella of symmetry statements. And again, suggests that a generalized Hooft paradigm with the symmetry is capable of explaining more features than just using the ordinary symmetries. So let me leave you with that, and we'll wrap up for today. What I want to start with next lecture that we'll do tomorrow is to turn to the class of symmetries that have really been understood systematically and explored over the last decade, which are global symmetries, but they are what are known, again, as higher form or generalized symmetries. These, again, are in some sense the thing that underpins the generalized Landau paradigm, but we're now going to see tomorrow, starting tomorrow, how they also can be relevant for generalized in the Hooft paradigm and tell us new things about particle physics. But in the meantime, thanks very much for your time this morning.